One of the most important applications of calculus is finding maximum and minimum values of a function. In other words, we would like to know what inputs give you the largest or the smallest outputs. So to start our study of maximum and minimum values, we'll start with a couple of definitions. So suppose that you have a function f of x, which is defined on some domain D. D might be the whole real line, or it might be just a sort of a subset of it. So then we say that f has an absolute maximum at x equals a if f of a is at least as big as all of the other outputs for all x in the domain. And then we'll say that f has a local maximum at x equals a. Well, if f of a is higher than all other outputs for x values that are close to a. And of course, you can change the word maximum to minimum if you change the greater than signs to less than or equal than signs. So let's just draw an example function to show what we're kind of talking about. For example, let's say that your function graph looks something like this. Maybe it comes down from up really high, a couple little wobbles here, and we're going to imagine that the graph kind of continues on forever. So that in this case, we're assuming that the domain is the whole real line. So the absolute minimum in this case is the actual lowest point. So on this graph, that's right there. This point over here is not the lowest point overall, but it forms kind of a natural valley in my function. This is what we mean by a local minimum. Essentially, if you are standing at the local minimum, then any motion in either direction will cause you to go to larger values. Similarly, this peak right here is a local maximum. Notice that in this case, this function has no absolute maximum, because the function continues to higher and higher values. So there just isn't any single highest value. So this is one of the first things we have to figure out how to deal with. Not every function has an absolute maximum or an absolute minimum. So how can we know if there even exists such a thing? In fact, if you look at functions that aren't continuous, you have all kinds of funny things that can happen. Maybe let me just show you one example. So suppose that you have a function graph that looks something like this. Such that where the peak sort of would normally be, you have a hole instead. Okay, so here we have a function where f of 2 is undefined. The limit as x approaches 2 of f of x is equal to 1, so that's where I put the hole. So this is a function that has no absolute maximum. That's not to say that you can get as high of a value as you want to, right? This is really a different case from the function that we saw up above here, where there was no absolute maximum because you could have outputs of 10 or 1,000 or 1,000,000. Here, you can get outputs of 0.9 or 0.99. You can get as close to 1 as you want to, but no input actually has an output of 1, and no output is actually the highest. Right? No matter how many 9s I tack on here, if I stop after 5 9s, well, then there's an output that has 6 9s instead that's even a little bit higher. So the presence of a discontinuity can make it a little tricky to have an absolute maximum or an absolute minimum. Okay, well, it turns out that there's a theorem that we call the extreme value theorem. Which says that if f is a continuous function on the closed interval from a to b, then it is guaranteed that f has an absolute maximum and an absolute minimum on that interval. Right, and I should point out there are two very important things here. It has to be a continuous function, as the example up here showed. And the other important thing is that it has to be on a closed interval from a to b. So, two things about this that are important are that it is bounded, for one thing. So it's not the whole real line, because in fact we saw up above, whoops, let's try that again. We saw up above that if you have a function that is defined on the whole real line, it's possible to have no absolute maximum just because the outputs are unbounded. So I need a bounded interval, but I also need it to be closed. Basically what happens is if you take the open interval from a to b, well, then sometimes it might happen that the absolute maximum sort of wants to be at one of the endpoints but can't. So let me show you what I mean by that. So let's take f of x to be the function x squared, and let's take the interval to be the open interval from 0 to 1. So then I have the usual bit of parabola here, but at x equals 1, well, I've kind of snipped that point away. I'm only allowing inputs that are between 0 and 1, but not including 0 or 1. So I have sort of a hole at both ends. And so it's the same problem that we saw before. There's no maximum here. There's kind of a ceiling. No output gets higher than 1. But it turns out that you can get as close to 1 as you want. So there's no absolute maximum here. Okay, but now in general, if you have a continuous function on a closed interval, maybe let me draw this up just a little bit higher here. So say here's the interval from a to b. Here's just some kind of random function. The absolute minimum is at this valley down here. And then the absolute maximum ends up happening at one of the endpoints. Okay, so we have a continuous function on a closed interval, and it does indeed have a minimum and a maximum. So now that we know by the extreme value theorem that such a maximum and minimum exists in a case like this, the question becomes, well, how do we actually find that maximum and minimum? And in order to look into that, next time we'll talk a little bit more about finding local maxes and mins first.